website for the next topic, and we always welcome topics as well. Feel free to email those to TriMech. You can email the topics for simulation content to myself, and I'll be happy to put something together. So today's topic is buckling analysis using SOLIDWORKS Simulation. And I'm going to walk you through a couple of different approaches we have to buckling analysis. Before I do that, I'm going to take just a couple minutes here to quickly give you an overview of our tools. A lot of times we come across people who not only aren't aware that we have simulation tools, but aren't aware of the extent of the tools that we have to offer. Obviously, there are express tools that are built into every seat of SOLIDWORKS, but that's just really a flyer. It's a notice to SOLIDWORKS users that we do have additional capabilities for simulation. We're going to focus on some of the tools inside of the FEA or the simulation package today. We also have tools for fluid flow and heat transfer, injection molding analysis, and sustainability. I'm going to come back to this slide in just a second. Our flow simulation tool, again, is for anyone who is in any application dealing with the movement of fluids, whether that be liquids or gases or heat transfer problems by way of conduction, convection, and radiation. Our plastics tool is an injection molding analysis tool that covers everything from basic questions a designer may need to ask when designing a part, all the way up to mold design. And then our sustainability tool is really an impact or environmental impact analysis tool for companies that are engaged in a green initiative, so to speak. So back to the simulation package that we're going to cover today. You may or may not be aware that our simulation tools are broken into 3 levels, similar to a lot of other products inside of SOLIDWORKS. We have our core simulation tool, which comes at the SOLIDWORKS premium level. We also have a simulation standard package that can be added to any seat of SOLIDWORKS. And that'll give you the basics, linear static analysis, stress, strain, deformation of parts and assemblies. It also includes a motion tool there. The simulation professional level contains 8 or so additional tools that are specific to different applications, one of them being buckling. So I'm going to start with the buckling tool that is inside of Simulation Professional. And we refer to that tool as a linear buckling analysis. Later I'm going to touch on the capability of our Simulation Premium tool, specifically the Nonlinear analysis tool, to do nonlinear buckling analysis, which is in reality a much more robust, accurate type of analysis to do. All right. So why do we consider buckling analysis? Buckling, much like fatigue, is something that is often disregarded or not taken into account, either because calculation of buckling would be difficult for real structures, much like fatigue would be, or the tools don't exist, such as there's no FEA tool in-house to be able to do the analysis, or it's just not considered. It doesn't come up as an important consideration when designing a structure. But in reality, structures often do buckle, and we see examples of this in the news from time to time. The types of structures that tend to buckle are slender, tall, or long types of structures that have compressive loading. And as I said earlier, buckling may be the primary failure mode. Buckling may occur before material yield, so you may design a structure and do some preliminary stress calculations to determine whether you have a certain safety factor from a structural standpoint without regarding your buckling load factor or the safety factor in terms of buckling. So a structure, particularly a tall, slender structure or long, that's under compressive loading may actually fail due to buckling well before material stress reaches the yield point. Also, buckling calculations tend to be very generic in that we have calculations in engineering text that will give us equations to be able to calculate buckling load factors for traditional, simple shapes. Let's say a column that's loaded in compression. However, when the situation becomes more realistic, in terms of the loading is not perfectly axial on the column, there's some side load or offset load, then the buckling load factor can plummet quickly. So our calculations could be extremely conservative, meaning they're over-predicting the buckling strength of the structure. And that's when we need a tool like SOLIDWORKS Simulation to help us gain insight into the real buckling load factor and buckling nodes. So here's some examples of different slender columns or thin long columns or slender webs or shell type structures that have encountered buckling of different degrees. So we have some, columns like on the upper right picture that are undergoing buckling tests. That's something that we would typically think of when we think of buckling. But also we may have the silo, like in the bottom center picture, that may undergo buckling, or a webbed type of structural member that may undergo buckling as its main failure mode. And a lot of times that's not considered in the design of those types of structures. So buckling theory first came to be back in the mid-1700s by a Swiss mathematician, Euler, who derived this critical load or buckling calculation to determine how a structure tends to buckle or reach its critical load that would cause buckling or the onset of buckling in relation to different characteristics about the structure. So on the left, you see the force that the structure is exposed to. And that's the force that we're trying to determine, or what that force amplitude or magnitude would be to cause buckling on the left side of the equation. And then on the right side, we have some characteristics of the structure itself. And what we see right off is that the critical buckling force is proportional to the modulus of elasticity of the structure. So the stiffer the structure, the more resistance it has to buckling, which makes sense. Another thing is the term I here means the area moment of inertia, or a geometric property that describes the distribution of mass about a center axis of some type of shape. It could be a cylindrical pipe, it could be an I-beam, it could be a much more complex structure. It could be a silo or some type of complex webbed structural member. But the area moment of inertia describes how that mass in a cross-section of that structure is distributed. And you see again that the force, the buckling force, is proportional to the area moment of inertia. So as we increase either the stiffness or the area moment of inertia, we reduce the tendency of the structure to buckle. So the more slender the structure, or the more the mass is concentrated towards the axis, the more tendency it has to buckle. The bottom terms here are what we call the characteristic or effective length of the structure. Now the L is the actual physical length of the structure, but the K term is used to adjust the effective length of the structure resulting from the types of end connections that may occur. So your structure may be rigidly held at both ends while it's under compressive loading, like a support column. Or it may have another type of connection, like a pinned connection or a roller connection, depending on the reality of the structure itself. So as we reduce, or I'm sorry, increase the characteristic length, so we have a longer type of structure, or we have a certain end condition that through the term K adds length or effective length to that structure because we have some type of pinned or free or roller type of condition at the end. So the longer the effective length, the lower the critical load necessary to cause buckling of the structure. So as we just saw, the critical load is dependent on the elasticity of the material and not just the compressive strength of the material. So we're not concerned from a structural standpoint on how much the material itself can take before we start encountering shear or yield in the material. It's more a factor of the stiffness of the structure. It's also, as we said, proportional to the cross-section or moment of inertia. And the boundary conditions, as we said, affect the term K, or the effective length of the structure, reducing the force necessary. This screen gives us a kind of a graphical image of how different end conditions may affect buckling. So you see on the top of the structure, they have the different end conditions noted. So we have pinned, fixed, fixed at both ends, fixed at one end and pinned at another, and then fixed and free. And you can see the relative amount of weight that's necessary to cause buckling, and then the type of deformation that's occurring in each case, which we would call the buckling, the mode shape, the mode of buckling. So obviously the fixed condition on each end is the stiffest and most resistant to buckling. So as I mentioned, K is a factor that changes the effective length of the structure, thereby changing the critical load necessary to cause the onset of buckling. And some generic terms or values for this factor can be seen here. So with both ends fixed, we have a K of 0.5. With both ends pinned, we have a K of 1. All right. Increasing the tendency to buckle. One end fixed, the other end pinned, 0.7, somewhere in between. And then one end fixed and the other free is 2.0, all right, the greatest of the four cases in terms of reducing the buckling load factor. So these are equations that you might find in a textbook that you can apply, doing hand calculations to typical shapes, predictable geometry. But in reality, the world's not like that. We have structures that are much more complex than a column and loading usually. This stool is an example out of the Simulation Professional course, where we talk about linear buckling. So this type of geometry would be a little bit more difficult to apply hand calculations to. And on top of that, we have the different end conditions for the feet, and they may greatly affect how or when buckling may occur. So the use of an FEA tool now in engineering has allowed or enabled engineers to take much more complex geometry and be able to predict the onset of buckling much more effectively than they could in the past. Really, the more complex your design, the more engineers in the past had to rely on only physical testing, physical prototyping. Of course, that is still recommended for any case, but the idea, along with any other application inside of FEA or CFD or plastics analysis, is to be able to analyze these structures during the design of those structures, and then when you go to physical prototyping, you can be much more confident that the actual physical response is going to mirror what you have seen in your analysis. All right. So really, in a linear buckling study, we're solving an eigenvalue problem. So we're getting the eigenvalues and eigenvectors, which give us the buckling load factors and the associated buckling load shapes. And that's really what we're after. The buckling load factor, the eigenvalue for this problem, determines whether or not a structure is going to buckle for a given load. So in the results I'll show you shortly, when we're looking at the buckling load factor, that's really a multiple of the applied force that would be required to cause a structure to buckle. So if the buckling load factor is 1, what we're saying then is that the load that's applied to a structure is exactly appropriate to cause the onset of buckling. Now 1 is right on that line, so will it buckle or will it not? Here we're saying in this slide that it's safe, but really I would rather say that a buckling load factor of 1 is not safe. It's like a safety factor of 1. You're not giving any room for error. Of course, a buckling load factor, I'm sorry, I read the slide wrong. It said over 1. It's safe. Equals 1 is the onset of buckling. So that I would consider not safe, right? And then a buckling load factor under 1 means that the load that's applied has already exceeded the load necessary to cause buckling. So the structure is going to assume its first buckling load. It's going to collapse in a somewhat predictable manner. Another interesting extension of that is a negative buckling load factor. And this would happen if we have an applied load that is a tensor load as opposed to a compressive load. Now, structures don't collapse from buckling due to tensor loads. Tensor loads actually tend to increase the buckling strength or the stiffness of a structure. And it's very similar to a frequency study. If anyone has done frequency analysis, you know that if you put a structure in compression, the natural frequencies tend to decrease. If you put that same structure under a tensor load, the natural frequencies increase. And an easy way to think of that is in terms of a guitar string. As you put tension on that guitar string, the note that it creates, or the tone pitch, increases. As you reduce the tension on it, it goes down. It produces a lower pitch. So the same is true for frequency and for linear buckling analysis. So again, under tension, the structure is not going to buckle. But we need to think oftentimes of, well, what happens if that load is reversed for some reason? So really you just have to think of if it's reversed, where is that buckling load factor going to be? And it's negative. So buckling load factor less than -1, if reversed, will be greater than 1. So it'll be safe for this. The buckling load factor of -1, reversed, will be 1, which is the onset of buckling, not safe. And then a buckling load factor less than -1 would be a structure that has then failed or buckled if it's reversed. If you run a linear buckling study, you'll get 2 results out of it. One will be the buckling load factor, and one will be the associated mode shapes. Now, this is very similar, again, to a frequency analysis, where you would ask for a certain number of frequencies and a certain number of mode shapes for the frequency analysis. In the case of a linear buckling study, although it allows you to look at multiple buckling load factors, really it doesn't make much sense to look past the first mode, because once the buckling load factor has reached the first mode, the structure is going to assume that failure mode, and it's going to buckle, which not only doesn't make sense to look at what's going to happen as the next buckling factor because it's already failed, but after it's undergone buckling, you've now changed the structure dramatically, because buckling isn't a failure mode that's hard to see, like yield might be. Material yield in the structure and the associated deformation could be very small, difficult to pick up on until catastrophic failure occurs. Buckling, on the other hand, it's characterized by large deformations that occur transverse to the load direction. All right, so once buckling has occurred, the structure is now a new structure, and everything beyond that doesn't make much sense. So a linear buckling study is useful for predicting buckling up to the point, the onset of buckling for that first node predicted. So let's talk about some limitations then of linear buckling. Linear buckling can be done on parts or assemblies, but because it's a linear analysis, what we're taking into account is the original stiffness of the structure. And it's really a snapshot in terms of geometry and material and geometrical characteristics of the structure. So for that reason, we can't have any types of, or any type of connections or other boundary conditions in the structure that may change the stiffness of the structure. All right, so that means that we can't have no penetration contact conditions where two parts that were separated may be coming together or sliding across one another, because any change in the physical geometry is going to change the geometric stiffness of the component. I'm not talking about the stiffness of the materials themselves necessarily. I'm talking about the stiffness of the structure as a whole due to its geometry. All right, so in the case of a linear static or a linear buckling analysis, we can't have things like bolt connectors or no penetration contacts. We can't have large deformations. So if something is undergoing a lot of deformation before buckling occurs, that really discounts the accuracy of a linear buckling study. We also can't have nonlinear materials if they play a considerable role in the formation of the structure. So, you know, hyperelastic or certain plastic materials, if the material characteristics are very nonlinear, then linear buckling probably isn't a good fit. So I'm going to show you a couple of short little vignette demos here to describe how the two tools may work and the differences between them. All right. All right, let's start off with a fairly simple example, again, of this just a cylindrical column or a pole in compression. So in this first example, I've set up a linear buckling study, and that's fairly easy to do. We would just, inside of SOLIDWORKS Simulation, start a new study, pick buckling as the study type, give it a name, and hit create, and it would create our buckling study for us. Now, in the buckling study, it looks very similar to most other study types inside of SOLIDWORKS. We have our component where we can apply our material. In the case of a linear buckling study, it would be a linear material. It could have orthotropic material properties, but it's still linear. We have our connections, and if we need to apply connections, you notice we don't have bolts. We can use springs, bearings, spot welds. Under contact sets, we can really only use bonded and free contact. There's no option for no penetration because of the reasons I said earlier. Under fixtures, you know, we have all of our standard fixture types that we can use. I'm just going to fix the bottom of the pole, so we could assume that it's, you know, embedded in concrete, let's say. And then under forces, we have all of our traditional forces that we can use here. I'm just applying a uniform 100-pound compressive force to the top face of our pole. And it's using the entire top face of the pole. And an important note is that it's, not only using that entire top face, but it's aligned with the axis of the pole itself. So I've meshed it and I run it. Before I show you the results, let's take a look at the study properties. The first thing you'll see when you go into the study properties is a field asking you to input the number of buckling loads. Again, this is a very similar concept to a frequency analysis, where we're looking for what compressive force results in more or less a fundamental or first natural frequency of 0. You can think of it that way. So I'm just asking for the first buckling load because that's really the one that makes sense. All right. So when I run this study, and it runs very quickly, what I get is the mode plot, or the deformation plot. You might think of it as a deformation plot. And I also get a load factor that's shown up here in the study window, or the properties for the plot. So it's telling me the load factor is 41.5. So my 100-pound force would have to be multiplied by 41 times to cause the onset of buckling, as far as this study is predicting. So 4,100 pounds would give us this result. Now you'll also note that there's a legend on the side. This legend used to actually give units of deformation, but the legend really is meaningless. They've actually just changed it to kind of a relative scale, and that's really what it is. They could, for all practical purposes, do away with any numbers next to the scale and just give a colored bar. So all we're saying is that the top of the column is going to displace more than the bottom, right, while we're undergoing buckling. And that makes sense, right? So the buckling load of 41.5, we can also see that by right-clicking on the results folder and listing what they call the factor of safety, which is the buckling load factor. And again, we see the buckling load factor is 41.59. All right, let's do this same study as a nonlinear buckling study. The nonlinear buckling study is by far superior to a linear buckling study because of the following point. And I'm not trying to discredit or say that the linear buckling study is not useful. The linear buckling study is useful under care or caution, you could say. If you want to use the linear buckling study, make sure that the buckling load factor that it gives you is multiple times higher than necessary, because it is a non-conservative result. It's going to typically predict the buckling occurs after it would have occurred in reality, just because of the fact that buckling is a very nonlinear type of process. And the linear tool will give you some insight into buckling, how it's going to occur, what the magnitude the load is, but just keep in mind that it's non-conservative, and if you're using it in practice, you want to make sure that it's multiple times higher than your safety factor for structural failure due to yield. So if you have a safety factor of 5, as far as in terms of yield, and you have a buckling load factor of 20, that's fine. But if it comes down to a buckling load factor of 5 in a linear study, you better take a second look and maybe consider running a nonlinear buckling study on that. All right, so in a nonlinear buckling study, which I'll switch over to, the process again is similar. We're going to go create a new study, but this time I'm going to choose nonlinear as the study type. And we can run various types of nonlinear studies. And that could be just a structural study. There's different types of control methods. We go into all of this in the nonlinear class, but one of the topics we touch on is nonlinear buckling. All right, so the process of creating the nonlinear buckling study is simply to create a nonlinear study. When we do that, we have a nonlinear study here like we would see, and the first thing to note is we have the option to use some of the capability that exists in the nonlinear study, such as changing the material model to a different type. So we can now include things like post-yield behavior, plasticity effects, permanent deformation, hyperelastic materials, viscoelastic or nitinol materials. All right, so we can get into complex material models. We can also now use nonlinear contact or no penetration contact, like including bolt connectors. Under our contact sets, we have the ability to use no penetration, even shrink fit contact. All right. Otherwise, I'm applying the exact same boundary conditions. I fixed the bottom, and I'm applying a load of 100 pounds to the top. Now, the difference in the setup, and I'm not going to go into too much detail here, but in the nonlinear setup for the study, the process of creating a nonlinear version of this study is to use what we call an arc length control method. And without getting into too much detail, the arc length control method allows the software to step down a very complex equilibrium path by projecting what they call an arc along the force versus displacement equilibrium path and calculating the equilibrium point of the structure. And so we are just asking the software to study the structure until it reaches a certain maximum deformation. So we just essentially pull that out of thin air. Or you could run a structural study under 100-pound load or 1,000-pound load, see how much the structure deforms under that load, and then use that as a guide, or maybe multiply it times 2 in order to set up your buckling study. And then you just ask for a certain number of steps along that path, and you're done. It's fairly easy to set up, and it runs. It's actually a very robust type of study. It's not susceptible to the types of things that would cause other traditional types of nonlinear studies to fail. For instance, if a force control problem encountered a buckling point, it would fail and it would give you an error saying that it had encountered a buckling point, because it can no longer determine what's happening in the structure. All right, so let's get off that side topic then. So what we see here is we have the same types of results we're used to in other types of linear and nonlinear studies. So we can look at stress, displacement, strain, time history plots. Because it's a nonlinear study, we have full time history. And we can look at, let's say, a stress plot. So in addition to the stresses, we're again getting a load factor for the nonlinear component of this, the buckling component of this nonlinear study. And you'll notice it's pretty much dead on with the linear study, 41.5. So it's giving us the same answer as we got before, just in a more complex study. So what's the point? Well, the point is that this is a very predictable linear type of setup. We've got a slender column that's loaded on its axis. It's free on one end, pinned on the other. It's very easy to predict what's going to happen. So we get the same answer in either case. If we look at the response, this is something that we can get in a nonlinear study as opposed to just the linear study. We see the structure being loaded, and these little dots represent the time steps through the study. And then all of a sudden, right at about 41.58, the structure gives way and buckles. All right, it's a great picture of catastrophic buckling, and it's right at the linear buckling prediction. So that kind of validates our linear tool in with some degree for this particular study. I'm going to now switch over to another case of linear buckling, but now if I zoom in here for a second, this is the linear buckling. Let me switch to what I call the linear offset. Okay, so in this case, it's just a cloned study. Of my previous study was just cloned, so I right-click and I choose duplicate, copy the study, and apply it to another configuration. The only difference with this configuration is that I've projected a split line on the top of my column, and I have now applied this 100-pound force to only part of the column. And it's not right down the center of the column. It's about 60% of the way across the face. So then I run the study again and look at the result. So the linear buckling study gives me a load factor of 41.3 as opposed to 41.5, so it's down slightly. So offsetting the load has reduced by just a slight amount the buckling load factor, meaning that this structure will tend to buckle a little earlier than it would have with the uniform load across the face. Good enough. Let's take that same configuration and apply a nonlinear buckling study. Again, I just clone the study, modify the load so it's only on a partial face of the top, and all the other settings are the same, and we rerun and look at the buckling load factor here. Here we get well, it tells us at the end of the study we have a buckling load factor of 39.6, so not a tremendous amount different from linear, but it is less. All right, but if we look at the response graph over the study period, we see that it actually is quite different. Instead of a catastrophic buckling event, we're having more of a gradual buckling event, and really it's that last plot I showed you was just picking up the last data point here. So it's giving us a buckling load factor of 39.6 or 3,900 pounds. But in reality, you may say, well, I would consider buckling anything past 5 millimeters, so that's more down at around 20 as a load factor, or even less. All right, so the point here is that the more nonlinearity you introduce into the problem, the more the response is going to differ between linear and nonlinear buckling. And that's because the nonlinear tool is able to solve the problem in a series of incremental steps, and in each step it's updating the stiffness matrix or the stiffness of the structure due to changes in the geometry or even material stiffness. If we have a nonlinear stress strain curve, it's accounting for those changes during the analysis and can therefore predict with more accuracy the response. All right, I've got a couple other examples that I want to show you, but really I might focus on this plate example first. So this is a cylindrical shell, and this is actually a problem out of our nonlinear class, the training class for nonlinear. And what we want to do is take this section of shell and run a buckling load or buckling analysis on it and make the assumption that the shell is loaded here at the center. So we might have some kind of snap-through behavior. It's going to be supported at the straight edges on either side and free on the curved edges. We're actually going to do a core symmetry model of this because we can. It's a symmetric model, so we're going to cut it down, and I'll show you the setup here in a second. So let's switch over to a linear buckling study. And again, this is a quarter of the model. So this is the curved edge on the outside. This is the straight edge. And this is the other curved edge, the other straight edge. And this is the actual center of our sheet where we're going to apply our load. So we need to add some symmetry boundary conditions to the sides. We're also using shells because this is a thin structure, so not really part of the discussion here, but we're using shell elements. All right, so in terms of fixtures, we have a supported edge or a fixed edge on the end, and then a symmetry condition on the two cut faces. So the two faces that join the center vertex where we're going to load it have symmetry conditions. Then we've got a force of 250 newtons applied at the center of our sheet. So we mesh it and run it. And this is what we're our tool is giving us as a prediction. So our first buckling mode, and this is the associated mode shape, is 27.8. Again, the color distribution is really just to give you a relative picture of the amount of deformation in this buckling mode. The actual numeric values should be disregarded. So this is what we see here for our linear buckling result for the quarter model. 27.8. Let's look then at a nonlinear version of the same model. So we're just cloning the study or duplicating it, using it in a nonlinear result. Again with arc length control, and we're asking for 100 arc steps, and we want to study this until it deforms 30 millimeters. Again, just you can run a stress analysis to see what that deformation would be and use it as a guideline. And that was actually done here. I skipped over it, but I'll show you. So this is looks like the displacement here is 0.5 millimeter under 250 Newton load, but we're extrapolating it up to 30 millimeters. All right, so let's take a look at the results here, and just again to remind ourselves, because I forget, I think it was 28 for the buckling load factor, 27.8 for the linear buckling load factor. All right, so let's take a look at the nonlinear buckling load factor. And this image let's see, this would be as we're looking at the deformation here, what you're seeing is this first buckling point is the one that's important to us. The nonlinear buckling tool is able to analyze continued multiple buckling modes past the first structure, the first buckling mode of the structure. This isn't the same as the multiple modes in the linear tool. The second, third, fourth, fifth, etc. mode in the linear tool are meaningless. But in reality, a structure may buckle once and then have a secondary buckling mode in a separate part of the structure, at a later point. So this is actually a snap-through condition because we're dealing with an arch, right? So initially the arch is collapsing, buckling through, and then we have the stress continuing to build. And if we were to follow this curve further, it would just go up and up and up until the part failed from material yield. So this is our first buckling point around 13.18, which is less than half of what the linear buckling tool predicts for this case. We can actually animate this. Let's look at the displacement plot. Slow this down a little bit. So keeping that graph in mind, what we see here is the initial buckling, and then the secondary buckling is this outside arched edge of the sheet. So we're pushing down, and then the secondary is this, and then the snap-through occurs, and then the force would continue to build because it's now in a stable, inverted configuration. So the linear buckling tool was pretty far off on this prediction. Now, if we take this even further and consider the full sheet with a non-symmetric loading case, so if we zoom in here to the center, you see what I've done is I've projected a split line down on the center, and this center point was where the initial load was. Okay, so it was a symmetric problem in terms of loading. The second case, the load has been moved out to a vertex slightly off-center to introduce some more nonlinearity to the problem. And the force has been quadrupled because now this is no longer a quarter symmetry problem. We're looking at the full sheet, so it's actually an equivalent force of 1,000 newtons. All right, so running the study again for 30 millimeters and looking at the results, we see at the end we have I don't want this to confuse you, this is actually the final plot step in the study. So this is the end of the analysis, and it's just telling us what the load factor is at this particular plot step, which is negative 8.5. The reason it's negative is because the structure has now reached a stable platform from a buckling standpoint. It's been inverted, and it can't buckle anymore. It's just the load's going to continue to build until the sheet fails due to yield. So if I was to actually edit the definition of this displacement plot, I can scroll through the different plot steps. And you see we start out at -8, we go down to -1, and then we start off we go into the positive values. So let's take a look at the response here. This is a little bit more complex. I'll just turn on the dots to show us the time steps, which is interesting to see because as we're progressing, so the part is being loaded, calculations, 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 and then the software detects that it's starting to enter a buckling mode, so it reduces the period between the time steps to be able to calculate what's happening. So this is fairly complex. So we're starting to buckle, and then it goes into buckling. This is the outer edges of the sheet going into a secondary buckling mode. It then reaches this kind of unstable point of equilibrium where we have this snap through, and then the displacement decreases again as the buckling continues. So our initial or greatest buckling load factor is about 11.64, so less than even the nonlinear symmetric case, which you would expect because any type of non-symmetric loading tends to reduce buckling or the buckling load factor in structures. So let's take a look at a displacement plot, do a little video here. This is kind of interesting. So you see, and I'll replay this, the green area is the part that's displacing the most, right? And then the yellow and red. So initially, the deformation occurs at the center of the sheet where the load is. And then you see it become unstable and wobble off from one side to the other. And it's biased towards the side where the load is. So the green is now progressing to the left. You see the structure kind of bobble there on the side for a second. It comes up and then down and then kind of commits to buckling on one side, and then the other side of the structure is pulled with it. And then the little shaking there at the end is just because it's reached a stable configuration, and the load is just increasing on it. So this type of buckling behavior cannot be captured in a linear study accurately. So yes, the linear study is useful, but it simply predicts the eigenvalues in a manner similar to a frequency analysis based on a constant stiffness in the structure, and gives you a result. And you have to take that result with a grain of salt, and understand that it's conservative, whereas a nonlinear study has much more capability to be able to track the behavior. Okay, I do have a couple other examples. I'm just going to quickly maybe bring them up in the last few moments, and then we're going to take some questions. I have several of them. Here's a container. Where we've run some stress, linear and nonlinear buckling studies. So here's a linear buckling study, and let's see, this is the stress study. Even the stress study gives us an indication of where buckling may, the onset of buckling may occur. Here, using the second principal stress plot, we can identify the compressive areas of the model, and this is actually where the buckling would occur. Let me see. Okay, well, I guess I don't have the linear buckling result here. This is the nonlinear, and again, this is kind of a, there's no catastrophic buckling mode here. Here you get kind of a good picture of what's happening. Buckling's occurring there at that compressive area. So nothing different about this study other than the structure is a little bit more complex, right? But again, it brings us further away from the capabilities of the linear buckling tool and into a full nonlinear study where we can not only use nonlinear materials for this plastic jug, take into account the nonlinear stress strain characteristics, but also all the nonlinear buckling elements that would apply here. The change of stiffness as this relatively complex structure is undergoing buckling. So that brings me to the end of my time. I'm going to open it up for questions. If you all are new to GoToMeeting, there's a question panel on the right-hand side where you can type in some questions. I don't see any right now. We'll give you a couple minutes of questions, and then we'll call it a day. While I'm waiting for questions, there's a couple more slides I didn't get to. These points are just things that would kind of preclude a linear buckling analysis from the start. Any type of inelastic or nonlinear materials, obviously, you're further away from a linear response. Also, if the load direction or magnitude changes during the analysis, that's also, a no-go for a linear study, because the linear study is assuming that the conditions at the beginning of the study are the same conditions at the end of the study. Not only stiffness, but also load, magnitude, and direction. And then any large displacements. We touched on that earlier. If there are large displacements in the structure before buckling, then you'd really need a nonlinear study to begin with. So please let us know if you're interested in participating in our success story program. We're always looking for case studies from the field. So SOLIDWORKS is always looking for case studies from the field as well. Contact us if you'd be interested. We will work with you to put together a quick and easy case study which will help us demonstrate the use of these tools and also allow you to get some exposure for your company. If you need one of our engineers to come visit, we do customer care visits continuously. We'd be happy to come and pay you a visit and look over your applications. It gives you some tips and tricks that may help you in your day-to-day practice. All right, it doesn't look like we have any questions, but if you'd like to send me an email or give me a call, please feel free to do so. My information is on the screen. Otherwise, we'll look forward to seeing you in a future webcast or at one of our live events.
All right. Thanks, everyone, and have a great day. Bye-bye.